the minefield of natural gas below the seabed. It's a recipe for disaster.
My first reaction was, maybe this was not a suitable location to build a bridge.
Driving piles into the gas deposit is extremely hazardous. The uncontrolled eruption of gas could undermine the bridge's foundation. A stray spark could ignite the gas and fuel a catastrophic explosion. Each time the team drives in a pile, it could spell disaster. Construction is put on hold until they can find a solution.
We were very worried. If, say, the natural gas problem couldn't be overcome, it would then bring harm to our construction and also the lifetime of the bridge.
The greatest threat comes from pockets of gas that are stored at the highest pressure. These pockets can pop like a balloon, erupting with devastating force. But after careful analysis of the gas field and consultation with leading experts, engineers come up with a solution.
We call it controlled gas release. We pick the most concentrated areas of the gas, then we drill holes down there, releasing the gas.
Small pipes are drilled into the gas deposit and fitted with pressure valves. The gas is slowly released until the pressure is low enough that the gas no longer poses a risk to the bridge. It's an ingenious solution that enables the engineers to go through the minefield, not around it. And the project is back on its feet. To build the world's longest transoceanic bridge, they must first drive 6,000 steel piles into the seafloor.
For the foundations of the bridge, we mainly depend on the steel piles. The steel piles for the bridge foundations are not replaceable.
Each pile must stand up to being hammered 80 meters into the rocky seabed and endure decades of exposure to salt water. It's a tall order, and there's no room for failure. To ensure success, they decide to custom build special factories near the construction site to make these extraordinary piles. Here, sheets of steel, 22 millimeters thick, are rolled into giant tubes, 1.5 meters wide and almost 90 meters long. Each tube is arc welded twice as it forms. First from the inside and then from the outside. They use a special copper-plated alloy to weld the steel together. Copper is a superconductor. It increases the temperature of the welding wire. When finished, the copper simply cracks off. Weighing in at close to 70 tons, each colossal pile takes 40 minutes to roll and weld. These are the longest and strongest steel piles ever used in a construction project in China. But these mighty steel pillars will be reduced to rust and rubble if nature gets its way. The piles stored on shore are rusting before they even make it to the water.
For this particular bridge, its design life is 100 years. What that means is the material that we use should be able to last 100 years with the least amount of maintenance and the least amount of inspection.
For the piles to last the test of time, the team must protect the steel from the elements. The process is costly and time-consuming. First, the piles are run through a machine that blasts the rust from their surface. Then they continue into another mammoth machine that coats them with an anti-corrosive preparation called fusion-bonded epoxy. To seal in the epoxy, the coating is heated to a sizzling 250 degrees Celsius. The temperature is crucial. Any significant drop and the seal will fail. Workers must constantly check the temperature using infrared sensors. But the team is confident that the piles are now ready for whatever Hangzhou Bay throws at them.
The steel piles designed by us will last for 100 years.
To speed construction, the team is building the bridge from the south and north sides of the bay at the same time. These separate stages must join with absolute precision. The placement and alignment of the piles is crucial to success. Traditionally, bridge builders use visual surveying to pinpoint where a pile must go. But with a bridge 36 kilometers long and an environment prone to torrential rain and heavy mist, the engineers will need to find another option. GPS, or Global Positioning Systems, use satellites to calculate positions accurate to a matter of centimeters. In the case of the Hangzhou Bay Bridge, GPS reference stations are set up on land. Experts from Trimble Navigation design an integrated GPS system for the bridge builders. Base stations on either side of the bay communicate with orbiting satellites to create a triangulated reference grid. Each pile is given a unique fixed address based on its latitude and longitude. When it's time to place the pile, GPS receivers on the pile driver locate that fixed address.
On the piling barges, they have two GPS, which actually reference to the base station out on the shore. So this power barge is able to navigate to the power positions, roughly. And once it gets close to the point, anchor is dropped and it's winched to its exact position. And once it's there, the power will be dropped. It really revolutionized the way construction work is being carried out. It really changed the way we work.
With this high-tech GPS system, the two ends of the bridge should meet precisely. 2.5 years after the approval of the design, the first pile is sunk into the sediment. But with thousands of piles still to go, there's no time to waste. To drive 6,000 piles into the seabed, they'll need a massive sledgehammer mounted on a monster ship. This enormous floating pile driver has been purpose-built. The piston drives the pile into the seabed with a force of 250 tons per meter. With each tremendous impact, the 28-ton hammer rams the pile deeper and deeper into the seabed. It takes more than 2 hours to drive in each giant 90-meter pile. The bridge is starting to take shape. But the piles are only the first phase of the bridge foundation. The team must now construct concrete piers to support the bridge. And once again, the bay's corrosive environment spells trouble.
For bridges of this scale, there are basically two materials, steel and concrete. Concrete, by its very nature, will actually require less maintenance than steel. But concrete also, we have found, does not have durability unless it is done properly.